Figure 4 shows a sketch of part of the curve C with parametric equations x equals 3 theta times sine theta and y equals sec theta all cubed. The point P, that's K8, lies on the curve C where K is a constant, and the first thing we have to do is find the exact value of K, so that is the x coordinate of point P. Well, we know that the y coordinate is 8, so we can use y equals sec cubed theta, set y equal to 8, and then we can solve this equation to find the value of theta at the point P to start with. So if we cube root both sides, the cube root of 8 is 2. So now we have 2 equals sec theta, and sec theta is 1 over cos theta. So if I multiply the cos theta up to the left and divide by 2, I get cos theta as a half. If cos theta equals a half, then the first value we get for theta is 60 degrees or pi by 3. Now if we check the range of values for theta, we can see from this inequality here that theta is between 0 and pi by 2. So theta being pi by 3 is the only solution to cos theta equals a half that is within this range. So that must be the theta value that we're after. Now that we know what theta is at that point, we can figure out what the x coordinate is going to be, because we have the equation in the opening question that the x coordinate is given by 3 theta multiplied by sine theta. And now we're going to substitute in theta is pi by 3. So that gives us 3 times by pi by 3 times by the sine of pi by 3. The 3 times pi by 3 cancels to pi, and sine of pi by 3, or sine of 60 degrees, is root 3 over 2. So here is our final value of K. We can say K is equal to root 3 over 2 multiplied by pi, and we were asked to give K as an exact value, so we should leave it like that. Next we're given some information about the finite region R, and then we are asked in part B to show that the area of R can be expressed in the particular form given. And when we look at that form, we see that it is an integral of a function written in terms of theta, so that's the parametric variable with respect to theta. So we're looking at parametric integration here. So my suggestion is that we always start from where that comes from, which is that region R would be defined by summing up from 0 to k, so these would be x values, of y defined as a function of x, and we'd be integrating with respect to x. Then from here we rewrite this in terms of theta. So what we would want this time is values for the limits, lower and upper limits, that were in terms of theta, so I'll leave those blank for a moment. Y can be kept this time, y will be written as a function of theta, and the dx will be replaced with dx by d theta multiplied by d theta. Now we are going to have to work out what those limits are, but for the moment we don't know what they are, so when we have an expression that we're integrating that's written in terms of theta, and then we're integrating with respect to theta, but our limits are not yet in terms of theta, we should record what variable they are in terms of. So our limits of 0 and k are x limits, and so long as we write x equals at the bottom and top, that will be totally clear. So now what I'm going to be doing is I'm going to be rewriting this line of work, but making sure that everything is in terms of theta as I work along. So I'm integrating, and the first thing I need is this lower limit, which is currently x equals 0. I need that to be written in terms of theta. So I'm going to work to the side so that this doesn't ruin the flow of my work that's following down the page. I want these equal signs to line up underneath each other. So let's move to the side, and we can even box off the work to make it even more clear that this is a kind of side working. So using the equation that the x-coordinate is given by 3 theta multiplied by sine theta, and saying now that we're interested in when x is 0, what value of theta matches to that, we get this equation to solve. So the first value of theta that jumps out at us is theta being 0. And of course, if we think about substituting that in everywhere, sine 0 would be 0. So we'd end up with 3 times 0 times 0, which is definitely 0. So that is one solution. It's also within the range of theta values between 0 and pi by 2. If we thought about other solutions to this equation, they would be other places where sine theta equals 0. And while there are infinitely many solutions to that equation, none of them would fall within the range 0 to pi by 2. So we are saying that the theta value that we're interested in on our diagram when x is 0 is theta being 0. And so we can write just 0 here. Now everything's going to be in terms of theta, so anyone who looks at this work will assume that this 0 that I've just written is a theta value. The second one I'm after is the value of theta that matches with the x-coordinate being k. And if you have a look at the diagram, we've already labelled that on. When x was k, we had a theta value of pi by 3. So that's what goes at the top here. The next thing we need is y written as a function of theta, and we have that from our opening information. Y is equal to sec cubed theta. Now we need dx by d theta, so that's some more side working out for us. We know that x is equal to 3 theta sine theta. We need to find dx by d theta. We're going to use the product rule here, with 3 theta as a u and sine theta as v. So we have 3 theta multiplied by what sine theta differentiates to, which is cos theta, plus sine theta multiplied by what 3 theta differentiates to, which is 3. So there is our dx by d theta, and that needs to go in next. And that y is being multiplied by the whole of dx by d theta. And because it's a 2-term expression, we'll have to put it in a bracket to make sure that everything is being multiplied. And then we have the d theta at the end. So that's what I've got so far. Now this is a good time to pause and see what's looking similar between what I've written and what I'm trying to get to. So when I do show that questions, I like to get a certain distance through and then start to have a think about what's matching. So what's good news is that I've got my d theta at the end here. I have an integral with limits, which was one of the things that I was going to need to find. I've got a sec cubed theta. The question seems to have sec squared thetas in it, so that would suggest that one of these is going to get lost in with this stuff, because you'll see that I've got a factorised, I've got this multiplied by this, whereas the one we're looking for just has 2 terms. And the other thing I notice is that the question format has lambda, which is a constant, sitting on the outside. Well, I can see what that constant must be. Actually, that must be the 3 in here. So that gives me an idea about what to do. I can start by pulling the 3 out. And secondly, I can look at expanding the bracket, remembering that I want sec squared of this sec cubed to remain, but I want one of them to not be there anymore. So as I multiply out, I'm going to start by thinking about sec cubed theta times theta cos theta. So I'll have the theta, and then I want sec squared of this sec cubed to stay. I've also got this cos theta here, and then this sec cubed theta means I have an additional sec that I need in here as well. And just leave it like that for a moment. And then for my second term, when I multiply out, again I want the sec cubed theta, I want a sec squared of it to show up. The other part the third part, the third sec theta. I want that to disappear somehow, and I've also got the sine theta to worry about, and that's all with respect to theta. And because I've got two terms, I can bracket this. It looks a bit neater for showing that that whole lot is being integrated with respect to theta. Now let's see if things are going to simplify how we want them to. If they do, that's going to confirm to us that we've done the right thing. So I've got theta, sec squared theta, and now I need to think about what these make together. So sec theta is 1 over cos theta. So if I multiply that by cos theta, it's going to collapse to a 1. So I've just got theta sec squared theta, which is exactly what I want. So I can move on to my second term. I've got a sec squared theta here, and then I've got a sec theta times a sine theta. Now sec theta is 1 over cos theta, so if I multiply that by sine theta, I'm going to get sine theta over cos theta. And sine theta over cos theta is tan theta, and when I look back at the question, that is also what I wanted. So I have now managed to get my work into the correct form. I have determined the constants for lambda, alpha and beta, so I am finished, and I can write QED to say that I have completed my proof. Now for part C, we are told to hence use integration, so we've got to use what we've just done to find the exact value of the area R. We've basically got to do this integration. So I'm going to carry on down the page this time because we don't actually need any other information from the question. We just need to be able to carry out this integration that's been recorded here. Now this is one of the more difficult things I've seen students have to integrate in A-level maths. There's quite a lot to think about. What are we going to do here? And what first might come to your mind is considering whether you should factorize the sec theta out. Now, because you might spot that tan theta differentiates to sec squared theta, and you might remember that when we look for integration by recognition, that can be useful. I'm going to actually just include something to do with that for a second so that you can see why that doesn't actually work. So if I go for this, although tan theta differentiates to sec squared theta, that tan theta is not by itself, it's added with a theta. And if I differentiate theta plus tan theta with respect to theta, I would get 1 plus sec squared theta. And there is no one element here, and I certainly can't introduce it because of the effect that would have on multiplying out these brackets. So it is not, that recognition idea is not going to work for this question. At least not on the whole expression in one go. However, we can use that idea that tan theta differentiates to sec squared theta to help us differentiate the second term of this expression. So just to be clear, I'm saying that this term, the second one here that I'm highlighting in yellow, this one can be integrated by recognition using the fact that tan theta differentiates to sec squared theta. So that one will be okay. If we know how to integrate the second term, then we should have a think about how we could deal with this first term. This first term has a polynomial part to it, in this case a linear part, just theta, and it has a trigonometric part, the sec theta squared. Now when you have that combination, so something that's a polynomial and then something that's trigonometric and they're multiplied together, this is the time when we use integration by parts. So we could deal with that first term by using integration by parts, and then we could deal with the second term by using integration by recognition. Now that could all get pretty messy, and there's a 3 at the front of everything that we mustn't forget about. So we're going to work this piece of maths in bits, which I don't normally do, but for this question I'm going to because there's just so much going on. So let's start by working on integrating theta sec squared theta by using parts. So we're going to have u as theta because when we differentiate that, it becomes simpler. It turns into a constant 1. And we're going to let dv by d theta be sec squared theta, because often when we integrate trigonometric expressions, they don't get any more complex through the process of integration. So we have to think about what sec squared theta is going to integrate to. Now, I mentioned earlier that tan theta differentiates to sec squared theta, and that means that sec squared theta is going to integrate to tan theta. So I think it's arguable here that the integration that we've done has made the trigonometric expression get simpler. That often doesn't happen. It often just stays of equal complexity, the part that you're integrating. But this one's even better. It's actually got simpler. And the theta has got simpler through the differentiation process. So that's a really good sign that integration by parts is going to be successful. So let's follow the integration by parts formula and see what happens. Integrating theta times sec squared theta is going to be uv, so that's theta multiplied by tan theta, minus the integral of v times du d theta. So that will be 1 times tan theta with respect to theta, d theta. So this is what we've got now. The next step is to leave the theta tan theta where it is and to integrate tan theta. And it's at this stage that you need to remember what useful information is on the formula booklet. They tell you how to integrate tan theta and the reciprocal functions sec, cosec and cot. So you don't actually have to do this one from scratch. You can use what's on the formula sheet. And you will see that tan theta integrates to ln of sec theta. Now, because at this stage I'm doing indefinite integration, I'm going to put a plus c on. So we've managed to integrate the first term. Now let's have a look at the second one. Let's put a different colour for that. So this time we're interested in integrating sec squared theta multiplied by tan theta d theta. And we're going to use a guess and check type strategy. So we focus on what differentiates to what. It's tan theta that differentiates to sec squared theta. So focusing on tan theta, we're going to make a guess about what that would integrate to. So I'm going to put the power on it up. I'm going to make it tan theta all squared, or tan squared theta. Then I'm going to think about what would happen if I differentiated that with respect to theta, and I'd have to use chain rule. So I'm saying that I'm doing a guessing and then checking method, but you will see this in textbooks referred to as reverse chain rule, because after I make my guess of tan squared theta, I will need to use chain rule to differentiate it. The method for differentiating tan squared theta would be to multiply the power down, drop the power down by 1, so that would give me 2 tan theta. But because I've treated tan theta as if it's one variable, we've then got to multiply by what tan theta differentiates to, which is sec squared theta. Now, if we look at this the other way around, so that we think about it as an integration, we can now conclude that the integral of 2, and I'm going to swap the sec squared theta and tan theta around to make it look closer to my question. Sec squared theta tan theta with respect to theta would give me tan squared theta plus c, because I'd be integrating. Now, we didn't want to do that. We wanted to just integrate sec squared theta tan theta. As in, we wanted to express the function that is half of the one that we've just written about. And the result of that is that the integral will come out half the size. A half tan squared theta, and the constant will be half the size. We can call it some other constant k. So we can now conclude that the integral of sec squared theta tan theta with respect to theta is a half tan squared theta plus k. Now, this green parts and red parts together tell us the whole integral of the blue statement. So I'm going to rewrite that all the way down here so that I have space underneath. So we're finding area R which is equal to 3 lots of the integral from 0 to pi by 3 of theta sec squared theta plus sec squared theta tan theta d theta. We keep the 3 outside, open our square brackets. We know that the first term, theta sec squared theta, from our green working out, becomes theta tan theta minus ln mod sec theta. We don't need the plus c now because we're doing definite integration. And then we're going to add on the integral of the second term, sec squared theta tan theta, which, looking at our red working out, is a half tan squared theta, and again we don't need the constant. And we're evaluating that between 0 and pi by 3. Now we've just got to substitute in and make sure we don't make a mistake. So we've got 3 lots of all of this. First substituting in the pi by 3, that's pi by 3 tan pi by 3 minus ln mod sec pi by 3 plus a half tan of pi by 3 squared minus, and then we're going to sub in 0, so that's 0 times tan 0 minus the ln of sec 0 plus a half tan squared 0. Close curly brackets 2. Now let's start evaluating this stuff. It's so much that I'm going to keep my curly brackets and squares in just to make sure I don't make a mistake. Pi by 3 is 60 degrees. Tan of pi by 3 is root 3. So we've got pi by 3 times root 3 minus ln of, now sec of pi by 3, that's going to be 1 over the cos of pi by 3, cos of 60. Cos of 60 is a half, 1 over a half, or the reciprocal of a half, is 2. Modding 2 is still 2. So we're doing minus ln 2, then we're adding on a half multiplied by, we need tan of 60, which we said was root 3, and that tan of 60, root 3 is being squared. Root 3 squared is 3, so doing a half times 3. So that concludes what's in our first square brackets, minus. Now we've got a 0 times, well, tan of 0 is 0 times 0 is 0, so that first term is 0. Cos of 0 is 1, so sec of 0 is also 1. Mod of that is 1, and so we've got minus ln 1 here, but ln 1 is 0, so we should note that down now, I think, so we don't forget. And then at the end here we've got tan of 0, which is 0, square that is 0, times it by a half is 0. So actually all parts of this last substitution, none of them are there. Now this question does ask us for an exact, let me just check that, hence to find the exact value of area. Oh, that's right. So we do want to keep everything neat and tidy. It will probably help to multiply the 3 in because it will cancel out with this first 3 at the bottom of pi over 3. So if we multiply the 3 in, then the pi over 3 times 3 becomes pi, and then we're timesing that by root 3. So we've got root 3 times pi for our first term, then we've got minus 3 ln 2 for our second term, and then we've got 3 times 3, which is 9 over 2 for our third term. And that is our whole final answer. And just before I end this video, I just noticed one mistake in my earlier work, which was at the start of part C, when I was integrating theta times sec squared theta. I should have said that I was integrating with respect to theta, otherwise that doesn't really make sense.